keeping up with our motto, let learning be a joy and teaching a pleasure. Here we are with a remote teaching and learning process to bridge the gap. Happy learning, students.
Hello students, welcome back to the Thakur Vidya Mandir High School and Junior College online teaching module. Today we are starting with our solid state part 2. Students, in the previous class we have learned about matter, its type, that is solid, liquid and gas. Then we came on to solids, and in solids we have learned about crystalline solid and amorphous solid. Further we went on to the classification of crystalline solid. Now, in this particular class, we are going to see again in the continuation part of classification of crystalline solid, we are going to learn about ionic solid, metallic solid, covalent solids, anisotropy, that is a phenomena, and unit cells of 2 and 3 dimensional lattice. Coming to next, ionic solids. Ionic solids are crystalline salts formed by the three-dimensional arrangement of the cation and anion bound by electrostatic forces. As you can see in the diagram on the right hand side, it is an ionic crystal which is having cations and anion in it. Two types of electrostatic forces are present. One is the force of attraction between the ions carrying opposite charges, and the other is the force of repulsion between the ions carrying the same charge. The arrangement of the ion depends upon the following factors like size of the cation and anion, the charges on the anion. Next, coming to the characteristics of ionic solid. These solids are hard and brittle in nature. They have high melting and boiling points. Since the ions are not free to move about, they are electrical insulators. However, in the molten or fused state, or when dissolved in water, the ions become free to move and they conduct electricity. When shearing force is applied, ionic crystal distort and the crystal structure is fractured. Example, sodium chloride. Moving on to the next, we have metallic solids. Metallic solids are crystalline solids formed by atoms of the same metallic element. Metals are orderly collection of positive ions in the sea of delocalized electron. These electrons are mobile and are evenly spread throughout the crystal. Each metal atom contributes one or more electron towards the sea of the mobile electrons. The force of attraction between these positively charged metallic ions and negatively charged sea of delocalized electron is called as the metallic bond. Metallic bonds are stronger than ionic and covalent bond. Moving on to the next characteristic of metallic solids. Metallic solids are good conductor of heat and electricity due to the presence of mobile electrons. Metallic solids are tougher than other solids due to the presence of strong metallic bond. The metallic solid contains several layers of metallic ions arranged over one another. Alloys can be formed by fusing the mixture of metals. Alloy shows all properties of metals. Metallic solid possesses metallic luster due to which the surface appears to be grey or silvery. Example, the surface of gold appears yellow whereas the surface of copper appears reddish. Even in the case of silver, it appears as silvery. Moving on to the next category of crystalline solid, we have covalent or network solid. Covalent solids are those in which the constant particles are non-metal atoms linked to the adjacent atoms by covalent bond throughout the crystal. A network of covalent bond is formed and the covalent solid also called as giant solids. Now let's check the characteristics of covalent solid. Depending upon the type of covalent bonding present between the atom, covalent solids are either hard or brittle. They have extremely high melting point. Covalent solids are good conductors of electricity if mobile electrons are available. Otherwise, they are insulator. Example, three allotropic forms of carbon, that is diamond, graphite and fullerene. Coming to the allotropes of carbon, we have the first example here as diamond. Diamond is an allotrope of carbon. It is used in jewelry and is the most precious crystal. Covalent bond between the carbon is sp3 hybridized and it has a giant continuous network. Diamond is very strong and hard due to the presence of strong covalent bond. It is the hardest material and has a very high melting point, that is 3550 degrees Celsius. If we check out the diagram, we can see the distance between two successive carbon atoms is 154 picometer. Because of this small distance, it is very difficult to break the bond, and so diamond is considered as the hardest and is being used for cutting glasses also. Coming to the next allotrope, we have graphite. Graphite is the allotrope of carbon in which each carbon atom is sp2 hybridized and form covalent bond with 3 other sp2 hybridized carbon atoms. This results in the formation of interlinked 6-membered ring. If you check carefully, pi bonds are formed between carbon atoms by utilizing half-filled unhybridized 2pz orbitals on each carbon atom. Layers of carbon atoms are formed. Electron present in the delocalized molecules of molecular orbital can move freely and conduct electricity. Hence, graphite is a good conductor of electricity. Whereas graphite is sufficiently hard due to the presence of relatively strong covalent bond, the adjacent layer of carbon atoms are held together by weak van der Waals forces of attraction. The layer of carbon atom in graphite can slide over each other. Hence, graphite is used as lubricant for reducing friction. It is used in ribbons using for printing in computers and typewriters. It is also used in lead pencils. Coming to the last allotrope of carbon, we have fullerene. Fullerene is an allotrope of carbon. It is also called as buckball or Buckminster fullerene. When a high power laser was focused on carbon, fullerene was formed. It has a formula C60 and a shape of a soccer ball. sp2 hybridization carbon atoms are being seen here. 60 carbon atoms are being placed in the form of hexagon and pentagon. Fullerene are present in carbon suits. Fullerene react with potassium to form K35C60. This compound is a semiconductor of electricity at 18 kelvins. It reacts with transition metal to form catalyst. Tubes made from fullerene and graphite are called as nanotubes. These are used as high strength material, electrical conductors, molecular sensors and semiconductors. Moving further, we have unit cell. What do you mean by a unit cell? A unit cell is the smallest repeating structural unit of a crystal solid. A crystalline solid can be obtained by repeating the unit cells n number of times in spaces of all directions. The line connecting center of the constituent particles are drawn to present a unit cell. The constituent particles can be an ion or an atom or a molecule of a crystalline solids. The point at the intersection of the lines which represent constituent particles are called as lattice point. These lattice points are arranged in a definite repeating pattern. Any one lattice point is identical to the number of other lattice points. Space lattice is the collection of all the points in the crystal having similar environments. Moving further, we have unit cell. What do you mean by a unit cell? A unit cell is the smallest repeating structural unit of a crystal solid. A crystalline solid can be obtained by repeating the unit cells n number of times in spaces of all directions. The line connecting center of the constituent particles are drawn to present a unit cell. The constituent particles can be an ion or an atom or a molecule of a crystalline solids. The point at the intersection of the lines which represent constituent particles are called as lattice point. These lattice points are arranged in a definite repeating pattern. Any one lattice point is identical to the number of other lattice points. Space lattice is the collection of all the points in the crystal having similar environments. Here we have a figure which illustrates a unit cell. When a unit cell are stacked together to generate the crystal, each unit cell shares its face, edge and corner with the neighboring unit cells. It is important to understand the geometric shape of a unit cell is same as that of a macroscopic crystal. For example, if the crystal has a cubic shape, the unit cell will also have the same constituent particles arranged to form a tiny cube. The dimension of unit cell along the three axes are denoted by the symbols as A, B and C. The angle between the axes are represented by the symbols alpha, beta and gamma similarly. student, here are the assignment question. Kindly go through it. Check out for the textbook on the link given below. Find out the answer and write in your notebook. Like this particular lecture, web links for other subject and other lectures are available on our college website and also on our YouTube channel. Till then, thank you. Stay home, stay safe.